Welcome back to Operating Systems Crashcast. I'm Victor, and today we're diving into Section 7.3, Methods for Handling Deadlocks. Sheila, are you ready to untangle this complex topic?
Absolutely, Victor. Before we start, let's quickly explain what a deadlock is for our listeners. Imagine a traffic intersection where cars from all directions are stuck because each is waiting for the others to move first. That's essentially what a deadlock is in computer systems. Processes waiting for resources held by each other, creating a standstill.
Great explanation, Sheila. Deadlocks are a critical issue in operating systems, and understanding how to handle them is crucial for any aspiring OS developer or system administrator. Let's start with an overview. There are 4 main approaches to dealing with deadlocks. Can you list them for our listeners?
Certainly. The 4 main methods for handling deadlocks are 1. Deadlock prevention 2. Deadlock avoidance 3. Deadlock detection and recovery 4. Ignoring the problem altogether. Each approach has its own strengths and weaknesses, and the choice depends on the specific needs of the system.
Great summary, Sheila. Let's start with deadlock prevention. This method ensures that at least one of the necessary conditions for a deadlock cannot occur. Can you elaborate on this approach?
Of course, Victor. Deadlock prevention works by eliminating one of the 4 conditions required for a deadlock: mutual exclusion, hold and wait, no preemption, or circular wait. For example, to prevent the hold and wait condition, we could require that a process request all the resources it needs at once and wait until all requests can be granted.
That's a good explanation. To use an analogy, it's like requiring everyone to place their entire order at a restaurant before any food is prepared, rather than ordering courses one at a time. This prevents the kitchen from getting stuck waiting for new orders while holding partially prepared meals.
Exactly. However, deadlock prevention can be quite restrictive and may lead to low resource utilization. It's like forcing everyone to order a full 3-course meal, even if they only want a salad.
Good point. Now, let's move on to deadlock avoidance. This method is less restrictive than prevention, but requires more information about resource usage. How does it work?
Deadlock avoidance involves carefully examining each resource request to ensure that granting it won't lead to a deadlock. The most well-known algorithm for this is called the banker's algorithm. It works by simulating the allocation of resources and checking if the system remains in a safe state after each allocation.
That sounds complex. Can you give us a real-world analogy to help our listeners understand?
Sure. Imagine a party planner organizing several events. They have a limited supply of tables, chairs, and decorations. Before committing resources to any event, the planner checks if they can still potentially fulfill all other events' needs. They only allocate resources if doing so keeps them in a safe state, where all events can eventually be completed.
That's a great analogy, Sheila. Now let's discuss deadlock detection and recovery. This approach allows deadlocks to occur, but aims to detect and resolve them. How does this work in practice?
In deadlock detection and recovery, the system periodically checks for deadlocks. If a deadlock is detected, the system can use various recovery techniques, such as terminating a process or taking away a resource, to break the deadlock.
Interesting. So it's like having a traffic controller who occasionally checks for gridlock in a city. If they spot a circular traffic jam, they might ask some cars to back up or take a different route to resolve the situation.
That's a perfect analogy, Victor. However, it's worth noting that deadlock detection and recovery can have significant overhead, especially in large systems with many resources and processes.
Absolutely. Now let's briefly touch on the last approach, ignoring the problem. It might sound counterintuitive, but there are situations where this strategy is used. Can you explain why?
Certainly. Some systems, like Unix and Windows, choose to ignore the possibility of deadlocks. This approach is based on the assumption that deadlocks occur rarely in practice, and the cost of prevention, avoidance, or detection may outweigh the risk. It's like choosing not to install expensive anti-theft devices in a very safe neighborhood.
That makes sense, especially for systems where deadlocks are infrequent or where the consequences of a deadlock are not catastrophic. To wrap up, can you give us a quick recap of the methods we've discussed?
Of course. We covered 4 methods for handling deadlocks. 1. Deadlock prevention, which eliminates one of the necessary conditions for deadlock. 2. Deadlock avoidance, which carefully manages resource allocation to maintain a safe state. 3. Deadlock detection and recovery, which allows deadlocks but aims to detect and resolve them. 4. Ignoring the problem, which is suitable for systems where deadlocks are rare or inconsequential. Each method has its pros and cons, and the choice depends on the specific requirements and constraints of the operating system.
Excellent summary, Sheila. That brings us to the end of today's episode on methods for handling deadlocks. Thanks to all our listeners for tuning in, and we'll see you next time on Operating Systems Crashcast.